next session on ANSYS Workbench tutorials. In this session, we will analyze the water bottle for its thermal analysis. We will analyze the water bottle which contains chilled water. So we will start by double clicking on steady state thermal module. First, we'll go to engineering data and double click. Engineering data sources. I am choosing stainless steel as one of the material, polyethylene as the second material, copper alloy as the third one, and aluminium alloy as the fourth one. Then I'll go to project and update project. Next I'll go to geometry and right click. Since I already have the model made with me, I'll directly import the geometry. Then I'll go to model and double click. We'll first go to geometry and select the body of the bottle and change the material to first say stainless steel. Also the cap I will change to stainless steel. Next I'll go to mesh and I'll generate the default size of the mesh. Next I'll go to steady state thermal. Now here I am going to insert temperature on the inner surface which is of chilled water. So for that I need to first suppress this cap. So we will go to geometry, we'll select the cap, right click here and hide body for some time. Then I'll go to steady state thermal, right click, insert temperature. On the inner surface I am going to add temperature. So I have selected all the faces inside, click on apply. I will give this inner temperature as 4 degrees Celsius, which is of chilled water. Then I'll right click and insert temperature on the outer surface. Now since this is subjected to ambience, I will give this temperature as say 25 degrees Celsius. I'll right click here and insert convection on the outer surface again. I'll give the value of film coefficient as say 20 watt per meter square degree Celsius, which is the film coefficient or convection coefficient of air. Ambient temperature as I've given is 25 degrees Celsius. Next I'll go to solution and right click, insert thermal temperature for all the bodies. Also I will right click and insert thermal total heat flux. Now this is also for the entire body. Now you want to see with the cap or without the cap, I leave the choice to you. So you can just go to this option, right click and show body, go to solution and solve. Now when you click here on temperature, you can see that the maximum temperature is 26.628 degrees Celsius. This is 4. Now you cannot see where the temperature is changing. So what you can do is you can just hide the cap for some time again. Click on temperature. Now you will see the variation of temperature on this bottle. So this is how you can check. Now if you want to use the cap, you can, but you won't be able to see these colors. Now you can click on animation and you can see the change of color over the bottle. Once you click on total heat flux, you can see the value of total heat flux is 97390 watt per meter square maximum. Minimum is 0.6498 watt per meter square. The minimum, as you can see, is somewhere here. Maximum is somewhere at the bottom end. So this is how you analyze for stainless steel as the material. Now in this case also, if you show the body and click on total heat flux, you will be able to see the colors on the outer surface, not on the inner surface. So we can as well keep this in suppress body mode or hide body. So once this is done, we will go to the body of the bottle and we will change the material to copper alloy. We'll go to solution and solve. Click on temperature, you will see the maximum value of temperature and the minimum value. Minimum will be 4 because that's what we have given. Maximum is showing on the outer side. Now you can see the total heat flux, it is 2.58 into 10 raised to 6 watt per meter square. Minimum is 7.1324. The total heat flux is more in copper as compared to stainless steel. So next we will change the material again and we will check for aluminium alloy now. Go to solution and solve once again. When we will click on temperature, we can again see the variation of temperature over the body. If you want, you can animate and check this result. Then we can click on total heat flux and see the value. It is 9.51 into 10 raised to 5 watt per meter square. So you will get these values based on the value of thermal conductivity of these materials. If you want to check that, you can go to engineering data, click on engineering data sources. These materials will be seen in one place. You can click on aluminium alloy and you can see the value of isotropic thermal conductivity, which is in this range, which you can see. Then you have for copper alloy 401. For polyethylene it is 0.28 and for stainless steel it is 15.1. So based on these you can judge who will lose the heat faster. So you can see for copper alloy it is the maximum, hence it will lose the highest amount of heat and total heat flux will be maximum for copper. Now once you're done with aluminium alloy, you can change it to plastic, that is polyethylene, and solve once again. Just click on temperature, you can see the variation of temperature and click on the total heat flux. You can see that the highest value is 1805.9 watt per meter square. Now this value, which is maximum in this analysis considering plastic, is showing you the least amongst the 4 materials because as you have seen the value of thermal conductivity of plastic is 0.28 watt per meter degree Celsius. Hence it is showing the minimum amount of heat flux. So by having the value of thermal conductivity and heat flux, you can decide which material you can use for your application. With this, I end the session. I hope you have understood the analysis. If you have any doubt, please write to me in the comment section. Don't forget to like, share and subscribe to the channel. Hit the bell icon for latest video updates. See you in the next session. Thank you.